All right, Dr. Bruce, the floor is yours.
Thank you, Alan. This is Robotics Society of Southern California, the July 2020 session. And I would like to introduce you all to a relatively new programming language called Julia. Most of you have probably not heard of this yet. I had not heard of it until recently. I've been taking the MIT linear algebra course online. They've updated it several times, and now they're promoting Julia as the programming language for the homework assignments and the various project assignments. Julia was created at MIT, so perhaps it's not a surprise that the MIT lecture courses are promoting its use, but let's talk about what Julia is. By way of a little background, we've programmed, and I've demonstrated robots at the club, programmed in BASIC, C++, Go, Python, and Lisp. As a general overview, I've tried to think, how can you describe the differences in these languages in a qualitative sort of way. BASIC is what it says. It's very basic. It's kind of like all of these things are tools in your toolkit, but BASIC is kind of like the basic tools that you first got when you got your first apartment and you got a little set of a hammer and a pliers and screwdriver. C++ and Go are when you get real professional hand tools. So you get those tools that just have a little more weight to them, and they feel a little more sturdy and capable. Python and Lisp are more like when you get power tools. And now all of a sudden you've got that power drill, and you've got that power saw, and you've got all kinds of different higher level equipment. Julia, I'm going to argue, is when you get the whole machine shop. And so suddenly you've got access to functionality that's similar to everything that goes into these other languages and others. In the past, I've talked about Leaf, the robot, the AI robot, differential drive. The main AI component of that was programmed in Lisp. Alex Brown programmed the motor interface controller in C, C++. We had a custom board for that. That was 20 years ago when we first developed Leaf. The next robot I presented was Chat. That was using TigerSlam for localization, navigation, path planning. And it was on an OmniWheel drive robot, although I really cheated and didn't use the OmniWheels. I used it kind of like a differential drive, but it worked pretty well, even though I was using OmniWheels. TigerSlam was programmed in Go, and I had a lot of help with interfacing that with Les, who was instrumental in helping me get that working. The C, C++ was something that I wrote for Arduino, and that served as the motor controller on that robot. The most recent one I've demonstrated is Hoot. That shows SlamTech for simultaneous localization mapping. The differential drive robot, again, it's an AI robot with the AI component. This time, I wrote it in Python and interfaced that with both the SlamTech control unit, which is in C, C++, and Alex Brown and Gary Malalepsy devised the interfaces for that SlamTech unit. And I also wrote C++ for the interface for an Arduino motor controller. So you can see that I've used different languages. We talked about them. I've given demos. One of the basic things at the lower level of motor controller has been the C++. And each of these has advantages and disadvantages. So the MIT group, both students, grad students, and professors got together, and this was their manifesto. They said they were power MATLAB users. They were Pythonistas, Ruby programmers, Perl hackers, R programmers. R is used for statistical packages. C is the desert island language. It's the language they would have if they were marooned on a desert island. Each one has trade-offs. Their plan was to use this for scientific computing, machine learning, large-scale linear algebra, parallel computing, and more. They wanted something that was easy to use, easy to learn, but with the speed of C, and borrowing things from languages like Lisp. This is not a object-oriented language. It's a functional programming language. It is something that uses functions and, like Lisp, has recursion, although most of the languages now have recursion built in, but I haven't seen too many people using that. It also treats the code as data. And by treating code as data, you can generate true macros like you do in Lisp. So if you need something in a language, you can build a new function and make it incorporated as part of the language dynamically in your program. So this is really the power of Lisp brought to this new Julia language. And it's, I think, going to really open up some interesting possibilities. They created this around 2012. It's still in development. These are the primary authors of the language. But because it's a language that treats code as data, Julia is written in Julia. And as you write programs, your programs can write Julia code. So where's the name come from? Not where you might expect. Julia comes from this fella, Gaston Julia, a French mathematician. Those are his dates: born in 1893, died in 1978. In 1914, he was a French soldier on the Western Front, in combat with the Germans, when some explosion occurred, some shrapnel took part of his face off, and after extensive reconstructive surgery, he was still left without a nose, so he ended up having to wear this mask the rest of his life. But he was a combat veteran in World War I and went on to win significant acclaim in mathematics, particularly with regard to Julia sets. Julia sets are functions using complex numbers, and if you plot them, they look like this. So this is one particular Julia set with one set of complex numbers. Here's another one.
I remember this from doing Mandelbrot set drawings back in the day. Yeah, Mandelbrot, and you'd pick an area of the Mandelbrot and create a Julia set from the Mandelbrot.
Very cool.
So it's perhaps not surprising, the person that really brought him to attention, his work was prior to Mandelbrot, but kind of forgotten, or people didn't really know what to do with it. And it was Mandelbrot that discovered his Julia sets and brought them forward as Mandelbrot fractals. So these are, if you look at them, there are a lot of them are very similar to Mandelbrot fractals. Julia, the programming language, 20 times faster than Python, 100 times faster than R, faster than MATLAB, and faster than Fortran. It's about the same speed as C. And since Lisp is compiled, it's similar in speed to Lisp. It's being used in data science, extensively in neural nets, artificial intelligence, particularly self-driving cars. We've heard a lot about those, and AI for humanoid robots. The areas that are using it are areas that employ big data, lots of huge data sets. So the insurance industry, the banking industry, economic modeling, airline scheduling, genetics, medical epidemiology, and climate science. Lots of number crunching, large data sets. Interestingly, the banking companies and the airline scheduling programs are so old that many of them go back and are still using COBOL and Fortran and code that people don't really understand anymore. So the banking industry and the airline industries are rewriting code for these mission critical applications, and they're finding that Julia is a perfect tool for them. So right now, these are some of the companies that are currently hiring Julia programmers. If you know Julia, these are companies where they could use your skills. Probably not too much of a surprise to see things like Amazon and Google, Facebook, Microsoft, NASA, Uber, because it's got a huge self-driving car project. It's one of the leaders in self-driving AI. So what does it look like? Well, I've blown up a couple of Julia programs for you to look at. And I'm also going to try to run a demo of some of these. But this is the Julia code for n factorial. And the nice thing I think about this is its readability. If you don't know any Julia, and I'm assuming you don't, you can see that I'm creating a function called n factorial, which takes one argument. There's an if statement. If n is 1, return 1. Otherwise, the definition of the function is n times n factorial of n minus 1. It's exactly what you would expect for a definition in words of what n factorial is, and it's built recursively.
Bruce, what does that double equal sign mean? Equal to?
Okay, the double equal is a conditional. If n is equal to 1, it's
Okay,
a conditional, then that returns true.
All right. Then it returns. Otherwise, it's going to do the what's below.
Yes.
Okay. So that's basically if n is equal to 1, basically.
If n is equal to 1, return a 1.
Otherwise, do this.
Otherwise,
do the function below and to return that value instead.
Yes, and keep doing this recursively until n gets down to 1, because you're subtracting 1.
Right. Okay. That's
Right?
sort of cool.
So if you put a 5 in here, the first time through, it's not 1. So it's 5 times n factorial of 4. Well, what's n factorial of 4? Well, it's not 1. So it's 4 times n factorial of 3. And the next time through, it's n factorial of 3 times 2. 2 times 1. Well, this time it's 1. So the function returns 1 all the way up the nest. So return 1 times 2. That returns that answer. And it keeps going all the way up the nest until you get back to the top level of 5. So it'd be 1 times 2 times 3 times 4 times 5. And that's the recursive definition. Show you that it also does linear algebra. And I'll show you this. This is a vector. And this is a vector. This vector happens to be an upright vector. And this is a 1 by 5 array or vector. This is a vector horizontal. So this is a 5 by 1 vector. And you take the dot product of A1 and V1 and you're going to get a scalar, single number. And I'll show you how that works. If I wanted to plot something, I could plot the sine, for example, from 0 to 2 pi. And what this says is calculate the sine from 0 to 2 pi, create a plot, and then display that plot. So this is the function. This is the Julia program to display a sine curve. I mean, think about trying to do that in C. It's probably not one line long. This one's a little more complicated, but only because I'm setting things up. So the first thing I do, I'm going to do a 3-dimensional surface plot. And I set X, one of the axes, to be from -6 to 6, with 100 steps in between. I'm going to set Y from -6 to 6 with 100 steps in between. And then arbitrarily, I've created a function, the square root of x squared plus y squared, and threw that into a sine wave. The function doesn't matter, except I'm just showing you we do exponentials, we add numbers, we're doing it over the entire range of x and y values, calculating square roots, throwing it into a sine curve. I'm going to plot it out in blue and lime. Those are my colors. And I'm going to throw it into a plot and have the x-axis, the y-axis, and the function. And I'm telling you it's going to be a surface plot. And these are the camera angles. We can play with that. So this is going to be a 3D plot, a surface plot. And again, 1, 2, 3, 4, 5 lines of code.
What's the C grad there?
What?
What was that C grad?
Well, this is the gradient for my curve. The curve is going to be whatever the results of this are. The minimum will be blue, the maximum will be lime, and there'll be a gradient from blue to lime on the surface plot. I'm just coloring it in.
Yeah. Also, there seems to be some assumptions are made there, like that the S function, when you say plot x, y, s, it must assume that s takes the two parameters x,
Got
y.
that? Yeah, got that from here, right?
But it had, if you were doing a two-dimensional plot, it would be different, obviously. But I guess you just showed that.
That's a two-dimensional plot.
Mm. Okay. It's cool.
Doesn't your camera need 3 dimensions for position?
I'm sorry, what, Les?
Doesn't your camera need a 3rd dimension for its position?
This is the angle that you're looking at the plot, and this is the elevation. So this is how you're looking at the plot that you generated. We'll play with those numbers.
Bruce, when you showed the display plot, how does it know how many points to actually generate to produce that plot?
It's up here. X is 100 points from -6 to 6. Y is 100 points from -6 to 6.
So that'd be 10 to the 4th points?
Yeah, for the surface, yeah,
Okay.
right. Which is what? It's 10,000?
Yeah, 1,000, 100 times 100.
So we got 10,000 points that are going to come out of this function and be plotted on the surface. 10,000 points.
Can you demo this code?
I'm going to try to. Let's see what happens. All right, this may be small. Can you see this screen?
Let's see demo time.
Yeah, just demo time.
Yeah, you need to share the other screen if you're, or
All
your
right.
entire screen.
Let me see if I can do that.
Right now, you're only sharing like one application, so it's only showing your picture slide thing. If you select show screen, it'll show the entire stuff in your screen. You can.
How's this?
Yeah, you have to stop sharing screen and then reshare.
I see. All right, let's do that. How's that?
Okay, we see
An IDE.
code.
Okay,
It's tiny.
I apologize for that. I don't know how to make it any bigger. Can you read it or not?
Try Control and the mouse wheel. That usually
Alright.
works.
Yeah, that's usually.
There you go.
That's like way too easy. All right. All right, so here's that function that I showed you for factorial. If n equal 1, return 1, so on. This is a really nice IDE for running Julia. And if I can write my code, save it by pushing the save button. I can run it. Now I'm running it and it's showing up down here in the REPL. REPL, R-E-P-L, is a term borrowed from Lisp. It stands for read, evaluate, print, and loop. And that's exactly what that, each line is processed. This code is compiled the REPL is an interpreter. So it will run interpreted code. If you can see now, can you see my cursor down here at the bottom?
Yes, we can.
Okay, so let's, for example, type what you would expect. 1 + 2, and that's in the interpreter. But I've compiled these lines of code, so now I can use them in the interpreter. So if my interpreter, I go back and I say, in fact, give it 5. And it calculates the factorial of 5, which is 120. So in this IDE, I am able to look at aspects of my code. There's on the right-hand side here, there's a lambda function called fact. There's another one called nfact. That's what I'm looking at right now. And the lambda indicates that it's a function. I've got some variables x and y. I have that answer that I printed out, which is 120, came out in my interpreter. But I wanted to show you there's shortcuts. So here's the function in 1, 2, 3, 4, 5 lines of code. The shortcut is you can use the logical and like in other programming languages, when you do a Boolean logical and, it starts and evaluates the first thing. And if this is going to return true, the first thing has to be true. If this returns false, it doesn't bother to return or evaluate any of the rest of the line of code. So if the first part is false, it will stop evaluating this line and go on to do the next line. This is a shorthand if statement. This doesn't get returned unless this part is true, in which case it will then check to see this part, which is the return statement, and break out of the function. This is a shorthand way of doing this block of if code. And now I've reduced my factorial to 2 lines. And we can check that again in here. Let's try 6. So 5 factorial was 120. Using my new factorial shorthand, 6 would be 5. 6 times 5 factorial, 720. So it checks out.
Dr. Bruce, we haven't talked about types. You're kind of implying that n is an integer. Is it a thing? You know, does it know that?
That's one of the nice things about Julia. It's a nice thing about Python. It's a nice thing about, especially about Lisp. It figures out the types for you.
So it's similar to Python, where depending on what you're putting into it, it'll turn it into that.
Yes, let's take a look again at that. 1 + 3. Those are integers. What it returned was an integer 4. If I do it again, and this time I'm putting in an integer 3, but a float 1, and I get out a float, it's figured out in order to make this work, I've got to be using floats. And so it automatically chooses whatever type it needs to make the math work. You can specify and you can force it just as you can in other languages. But normally that's one of the advantages is you don't have to do all those declaration statements. You'd have to declare all these variables in BASIC or in C.
Will it automatically cast as a float for division?
Yeah. So, well, I'm not sure what you meant automatically. Let's do one divide.
That answers my question. Thanks.
Yeah, okay.
Hey, Dr. Bruce, there's a question in chat from Chris.
Yes.
So for the stuff we've seen so far with the factorial function, is there anything in that that Julia processes implicitly in parallel, or is this processed traditionally in serial recursively?
I don't know the answer to that. That's a good question. It does certainly handle parallel processing. How you do that, at this point, I don't know the answer.
Okay, all right.
So that's a really good question. And you would want to be able to break it up into parts if you wanted to, but you'd also want it to do it automatically if it made sense. So I don't know how it handles that. I don't know the answer.
I think for a factorial function, that's an intrinsically serial thing because before the next function is called, you have to evaluate the previous one. So I don't think
Yes.
that you could parallelize a factorial function as written here.
Yeah, that's
Not
true too. That's true too. There's one other thing I just saw this, and so I want to try it. The double backslash is supposed to be fractions. And apparently it's not. We tried the other way around.
Is it like an escape character, the first one, or?
There we go. It's forward slash.
That's nice.
And what would be integer divide? Is that like div or something? div, like we want an integer divide.
I don't know the answer.
I'm sure they have one, but yeah, it's not.
1/3 is this. 1/3 might be this. Give me the same. No.
Wait a minute. 1/3 is 3.
Looks like it's an inverse.
It's an inverse.
Oh,
So yeah, you gotta be careful. That's an inverse. I don't know how you do the integer divide, but there's a way to do it.
try div, div. Say like 5 div 3.
You want me to do it like that?
Or I meant, well, maybe, yeah. Either that or 5 space div space 3.
Well, I don't think this. Oh,
That's
there you
it.
go.
That's it.
Wow, that's interesting.
And then
Jim,
you
that was an excellent guess.
also try mod 5,3.
Okay. Give me a second.
For the remainder.
Yeah.
There you go.
Yeah, I like languages.
Well, you have kind of illustrated that hopefully this is at least semi-intuitive. You can make some guesses that if you've come from other languages, some of your guesses are going to work. Some of them might throw you off, so you do have to be careful.
Yeah, are the precision to which it prints out a number, is that variable? Because like when you printed the 3, it came out like, I think it was 12 places. 1 divided by 3, like 3.
Yeah.
12 places. Because
I believe you can specify that the default here is, the default for integers is float, is integer, no, that's not right. That's a vector. The default is, because I'm on a 64-bit machine, the default is 64 bits. But I think they can do big nums with arbitrary precision.
I'm sure they have arbitrary precision as a package. They have to if they're going to do R and that kind of stuff.
Yeah.
You start doing.
Let's look at the linear algebra, and we'll run that one. And I've now defined a vector and another vector, which happens to be a vertical array, and the dot product. So if I come down here and look at V1, it tells me, because I didn't use commas, it is a 1x5 array or vector using integer 64. And it's a 1x5, it's 2-dimensional. If I look at A1, it's showing it vertically, 1, 2, 3, 4, 5. And it's an integer 64, and it's also a 1-dimensional vector. So if I now do the dot product and print that, and I can do one line at a time with this little lightning bolt symbol, and it printed out 55, which is the dot product of V1 and A1. Basically, it's, since I used the same numbers, basically you're multiplying each number against itself, so you're squaring it and then adding them all up, and you get a scalar number 55. So dot products, matrix algebra, inverse, determinants, trace, all of that is supported with the linear algebra package. Julia uses packages. Python uses libraries. Other programs use libraries. It's the same thing. So they're using, and you say using a particular package or library, and then you don't need to do the dot naming convention. I don't have to say linear algebra dot dot. I've used this, so it's pulled in all the functions, including dot, and all the other functions, matrix algebra functions. So using, and then you specify which packages you're going to use. Let's do a trig example. This time I'm using plots. This is the plotting program, plotting package. And this is the example I showed of the sine wave from 0 to 2 pi. I'm going to calculate it. I'm going to plot it. And then I'm going to display it. So let's see what happens when we do this one. And there it is. I can change it. We're going to make it 20. Oops.
In your syntax there, is 2 pi a fixed defined number, or is that actually 2 times pi?
It's times. You could put the times multiplier in here, but you don't actually have to. it recognizes, just as you do in algebra when you're writing things, if you write 20x, you don't have to put the multiplier in there. So we do 200 pi. There's 200 sine waves. You'll notice I'm hitting this lightning bolt, which runs one line at a time, which is great for debugging. If I wanted to run everything, I can hit the run all button. Let's do the lightning bolt, and we're back to doing a single sine wave. But you'll notice that when I did the plot, it calculated all the defaults for me. So it starts at 0 and goes to 2 pi on the x-axis, but it calculates the y-axis based on the results of the function, and then scales the display accordingly. You can set the parameters, but you don't have to. That's what makes it nice for getting in there and working with these examples. When you're developing code, you don't have to worry about the dimensions of your arrays. You don't have to worry about the type of your variables. So much of it is already done in default, but you could change it if you wanted to. So this came out as a blue line, and this is Y1, but I could change it a different color. I could put different plots onto the same graph and have them all be different colors. There's lots of things you can do with the plot package.
What if you want to leave the range at 2 pi and just make the frequency larger? You have to feed the sine function with some time parameter. So if you put brackets after sine and put I don't know, t or something.
I'm not sure what your question is, Sergey.
Well, imagine that you want to increase the frequency of the function on the oscilloscope. So your range in 6 milliseconds will be the same, but the frequency means that you are feeding the parameter, the time parameter to the sine,
okay,
with multiplier. So,
I understand what you're saying. This is a graph, not an oscilloscope, but I understand your question. I can show more cycles, right? But I'm not sure I understand what you're asking is about whether you could put a time element on that.
What's the horizontal resolution, I think is what he's getting at.
well, I mean, you can always define a separate function, for example, sine1.
Yeah.
And then that sine1 will call the sine with the multiplier. So
Yeah.
sine1 of the t, and then sine from 20t. But that's brute force. That's not a single liner.
And
Okay.
you just say two times, right there where it says plot, put a two sign, and that will change the frequency, right?
No, that will change amplitude.
I'm sorry, that's amplitude. So then it would be the input to sine. How do you change?
Yeah, this would be written differently, and I understand your question, but I'm not sure how you would change it. I'd have to go into the definitions. I don't know that.
Or like sine and then in
That's
parentheses
my
2x.
specialty. Tricky
That would be
question.
2x.
Sine of 2x, that would be introducing implicit x as a parameter, right? I mean, the interpreter has to know that x belongs to the horizontal axis.
Yeah,
Some of this might be more evident on the next example. Because I also used sine in this example, but it's the sine of the square root of this polynomial.
I think it does have implicit, seems like it has implicit things going on, variables.
Yeah. So this one, if you, and I'm not sure again, Sergey, this answers your question, but a different kind of example. This is a range from -6 to 6 on the x-axis, -6 to 6 on the y-axis. I'm calculating this x squared plus y squared, taking the square root and feeding that into sine. So this ends up being a whole range of individual numbers going into the sine function. And then we're going to plot that as a surface plot. So let's take a look at that and see if that helps at all. Besides, it's prettier. So here's a three-dimensional plot with 10,000 points on the surface of this plot. The bottom, as you can see from my gradient, the lower numbers, and here they are, -1 is blue, +1 is lime, and here's the gradient. So this is the color-coded gradient of this function. And someone was asking about these camera numbers. I'm looking at this at an angle. Here's the corner. Here's the back corner. I'm looking at an angle of 70 degrees, and at an elevation of 50, let's change the elevation to 0. And now you're looking at it head on, and you can't see the wall of the curve is obstructing your view. You're looking at the outside wall of this flower shape. So let's go to 7.
Similar to the sombrero, sombrero plot.
Yeah. I'm going to tilt it a little bit more.
Dr. Bruce, may I ask a question?
Yeah.
Okay, what are you planning to use this thing for? Looks like manipulate an image or something?
I'm sorry?
What are you planning to use this programming stuff for, may I ask?
The new programming language?
Yeah, what's the advantage of using this over something else?
Well, it's certainly a more powerful language than most of the things we've been using. And it allows you to get into data science, linear algebra, neural nets, and a lot of the number crunching that goes in with big data. So I don't know the answer to that yet, Tim. The question is whether I would use something like this for my next.
Well, I mean, I saw the list of people that were using it. I was curious why Disney wants to use something like this. What do they use it for?
I don't know. Good.
Now, does this cost you anything to get a hold of, or is it free to get a hold of?
This is all free.
Yeah, I just was wondering I came in late on this thing, so I just was wondering what what would they use this stuff thing, this programming language for? Oh, using linear algebra?
Anything using data analytics for big data.
Okay, I guess
So artificial intelligence, self-driving cars, humanoid robots. If they're looking at it for
that's
Google,
fine. That is fine what you're listening, but what do they use it for in those things? What is this? Is it the main programming brain language or what? What do they use it for?
Probably the same as Python, right? You know, Python is heavily used in machine learning and
Well, I mean, I haven't even learned how to use Python, let alone do anything with it.
right. But I'm just saying that this seems like it's in the same vein as what Python's being used for: big data, machine learning. That's what the courses are in Python. Maybe this is like the next or an aspiring language to handle that, to do the same things. But that all sorts of machine learning is done in Python, and TensorFlow and PyTorch are big you know, systems that use Python. And you can take a relatively quick course on Coursera just to get your feet wet in using Python. So I recommend those.
Okay,
yeah, so if you're going to be
Practical standpoint, from the practical standpoint, what you need in robotics is how you control the motors, for example. Is there a library like to connect to Raspberry Pi hat? Is there a way to open camera and look at the image, you know, and then you can process it? Is there a sample code for a known robotics platform? For example, NVIDIA provides Python for JetBot, but
yes.
I don't see any code in Julia for robots.
I obviously haven't gone into that. But to answer your question, yes, you can take images and then do neural net, convolutional neural net image processing. You can interface to OpenCV. You can interface to ROS. There are ROS cores for this. So you can program in a high level programming sense, like Python or Lisp, but it also lets you get down into the details like C. It also allows you to interface to both Python and C libraries. So if there's already a function that you like, and it's written in Python or it's written in C, you could just hook into that through Julia. So it lets you do, basically, Tim, it lets you do anything with any robot running on a full-scale computer, not a microcontroller. But you'd be able to write a program to do what I did in Leaf, to do what I did in Chat, to do what I did in Hoot, using Julia, and perhaps not needing the lower level interfaces. For example, in Chat, I had to write a Go language driver for the LiDAR. But you don't need to do that. You can do it write it in Julia.
may I try here?
What's that?
May I try to explain this to Tim in a different way?
Go right ahead.
Okay, Tim, think about a box that is like on your animatronics. You have a box that does the voice and moves the lips, right?
Okay.
Then you have a box that moves the limbs, right?
Okay.
Now, if you want your animatronics to do more than that, you add more boxes. What this language allows you to do is to have programming boxes. You can have a programming box that does the thinking, like a neural net. You can have a programming box that does driving the motors, like running one forward and one backwards and so on and so forth.
Mhm.
You can have another box that like runs a gripper. You can have another box that runs the camera, and another box that will integrate the camera information and the gripper information and the wheel information and the mapping information and produce the navigation stuff to get the robot to where it's supposed to go. And then you can have another box that's the overall controller that says, our mission is to go get a bottle out of the refrigerator.
Okay.
And so this language makes it easy to do all those things with just having one overall programming language that ties all the boxes together.
Okay.
So instead of having to write all the individual pieces, most of the information that you need is already constructed into the procedures that you can call directly from this language. For instance, if I were going to draw this graph that we just drew in C, I would have a procedure that does all the plotting. I would have a procedure that brings up the display. I'd have a procedure that labels the graph. I would have a procedure that does the graphic itself. And then I'd have to tie all that together and write it to the display. And it would be probably 11 or 1200 lines of code to do that. But he just did it here with what, 7 lines or 8 lines of code? Because this language already has a lot of those capabilities built into it, and you can access it by just saying plot.
Oh,
Okay, does that help?
a little bit.
My,
Yeah.
what I was gonna say,
I've learned so many different languages. I don't see the point of learning another one. And I'm just trying to figure out what the heck is the use for it.
Well, it's just higher level. And what happens as you go through the progression of languages, like Dr. Bruce showed at the front, is each language gets more and more powerful and tailored toward the job that you want the language to do.
So Tim, what languages do you currently know?
Well,
You
me?
said- Yeah.
Hold on. Well, let's see. I started out with Fortran. Got into basic, really heavy duty. Got into various machine languages for very microprocessors, starting with the 8008 and ending up with the 6502. And into the Arduino stuff. So, and then into some other embedded processor stuff. So.
Okay, so you would never, in your wildest dreams, attempt to do this program in assembly.
I'm sorry, Bruce?
You would never, in your wildest dreams, try to do this program in assembly.
No.
This would drive you absolutely crazy in assembly, right? Now, you
Probably.
might try to do it in C, which is what Les was talking about. And you could probably do this in C. And it would be 1,200 lines. And it would probably take you a week to get it to work.
Yeah, probably.
Here it is in 5 lines.
So what's the advantage of using this over Python? Because I know Python has a similar high-level approach.
Okay, now let me go on to my next thing here. I'm going to stop the share here for a second and come back with a different one.
Oh, and also I learned a weird language called Forth.
Called
Forth
what?
is good.
Huh? Forth, F-O-R-T-H.
Forth is good. Forth is great. It's fun.
I liked it because you can create your own functions and stuff.
Tim, you're talking my language. I love Forth.
Back in the day, I don't use it much.
Yeah. Imagine,
Processors that ran off of that stuff.
okay, imagine
There's
this
a
is
mouthful.
your equation.
Okay.
Now, I'll be real honest and tell you I have no idea what this says. But it's obviously an integral. There's a nabla operator. There's a dot product. This is the function that you're here's a function. This is the definition of the function. The function takes some parameter. It does a cross product. It's got some things squared. I don't know what all this means because I don't know what each of these things is. But here's the function. Well, two functions, right? Here's the function, and then they take the integral of this function. Wouldn't it be nice to be able to write things like this? Lambda equal 5.2 and a function called sigma. Well, in Julia, you can do that. These are just Unicode characters. So you create your functions using Unicode to map up with what all these things are. And you can overload functions to create cross products, dot products, integrals. And so, since you can write code in Julia using the special characters, these two functions get written like this in Julia. This is actually Julia code. Again, don't expect me to explain it other than here's the integral, here's the nabla operator. They're taking a derivative. These things have been defined in the programming language, but then when you need to use them, you just go ahead and use the symbols directly from your equation. So the mathematician can program in Julia. When I say higher level, I mean literally transliterating the equation that he wrote on paper and type it into the computer, and it runs.
That's pretty incredible. It's like MATLAB on steroids. And
for example, Bruce, I could take all Tesla's equations and write a program to turn the crank on all of them.
Yeah.
You could take your equation right from the LaTeX printout and put it in.
If you've defined all the functions, yes. So you don't code the math.
Mm-hmm.
The code is the math.
Ah.
So Bruce, that's really pretty, but how would you even go about typing that?
Yeah, that's the hard part.
Yeah.
Actually, it's not.
Or you can you could copy and paste from a, like I said, from a paper, a scientific paper. It would already be in that.
I'm gonna come back to the example here.
If you had to enter your own equation from scratch, might be a little hard.
See if I remember how you do this.
Mm-hmm. This has some possibilities. I might have to get a copy of this.
Dr. Bruce, how long has this program been around?
Since 2012.
Okay.
Yeah, it wasn't around when they first started with the Tesla code. All I had was MathCAD at the time.
It would be nice if they used the LaTeX. LaTeX is a whole language for scientific equations to print them.
Okay, so
really?
Let's take, can you see again down here at the, let's get rid of this.
Yeah, it looks like he was writing LaTeX.
It is.
That's what I would think, I would hope for.
So you type a backslash to get to the Unicode. It's Unicode. And lambda tab. And when I do lambda tab, it gives me the word. When I hit tab again, it gives me the symbol. And I can set that to be equal to 67. So now, what's the value for lambda? 67. I could make it into a function. I could do, there's 2 keystrokes to get it. It's equal to lambda plus 5. So I can use it just like any other variable name. I can use it like any other function name. And there's a whole library of functions already predefined using these kinds of symbols.
That's really
So
nice.
you can see how you would, using the Unicode symbols. I don't remember if there's and there's the whole list of all of them, of which there's kind of a lot.
Fourth root.
Fourth root, you want to do that?
Yeah, do the
Oops. Where were we? Fourth. Fourth root. Well, you have to type properly.
Does up arrow work on this to get to the previous line, previously entered line?
Oh, I'm getting a P in there. F-O-U.
Try one more time, see if we can get something.
That's weird.
I mean, you have to hit tab.
I did.
Yeah, it looks like that up arrow works.
Yeah, but if you go back to my Unicode.
Perhaps you need to type lambda and then fourth root.
But lambda is a separate Unicode. It's.
Let's do something here. There's square root.
That worked.
Yeah. So there's the square root. So I could define that, or it's actually already defined in some library.
That's pretty cool. You just have to know the name of the thing or their abbreviation.
Well, again, it's standard Unicode. So if you were looking at, there's ASCII, right?
I thought Unicode was for China and for various languages. These are more mathematical terms. I didn't think that's exactly, or Unicode. Maybe I'm wrong.
No, Unicode's like everything you can do. So let's.
Okay, it's a subset of Unicode for mathematical stuff. I mean, obviously, that's what's important here.
Jim, the mathematical symbols are just another version of iconic images. So it doesn't matter whether it's Chinese or math symbols or whatever.
Right, but there's a standard Roman letter equivalent with the backslash or whatever. There's a name for these that's standard in the Unicode definition, I hope.
Bruce, what do you plan to do with this language once you get better at it?
Program robots.
I can see where it will simplify code you could use. I'm not sure how you link it into the robot stuff, but You can see where it can simplify some code that would take longer to write it in some other language.
You do it the same way you do every other programming that we've done.
I think of this as the hybrid, you know, my breakdown of the robot is the low-level brain, mid-level brain, and high-level, right? The Arduino controller is the low-level, the mid-brain might be some other, you know, slightly more sophisticated, than the high-level is a Windows machine or Linux machine or Raspberry Pi, and that you know, runs the most sophisticated high-level language, and it sends the commands down to the lower-level brains via serial or I2C or something. Well, yeah, probably serial, but that's where it'd be useful because it has to crunch all the high, you know, the huge data, AI and stuff.
The point I think too, Jim, is if you're going to be doing a lot of data crunching, then you don't want to be switching languages if you can avoid it.
Okay.
This allows you to crunch as much data in Julia as you need because it does support large databases, parallel processing, and
So
all of that.
use it like for like maybe the higher functions or something.
Right. So here's some Unicode. There's pi, sigma, but there's also other things in Unicode. The yen, the euro, and anything you can basically put on latex is going to be available in Unicode.
And there's nothing stopping you from defining functions with any of those symbols arbitrarily?
Correct.
What Unicode does is it has 4 gig different characters available, and they're mapped to all kinds of things, from different languages to mathematical symbols, medical symbols, all kinds of stuff buried in there.
Well, I think my time's more than over, so I will thank you all for listening, and hopefully somebody else can do this next month.
Well, it sounds like I might want to get a whole language to mess around with it. So you download a copy off the internet somewhere, or
yeah,
is Julia?
Julia download, you'll find it.
Okay.
Geez, Bruce, I thought you were going to end up with a Julia plot, you know, at the end there. That would have been the obvious ending there.
Yeah.
That's got to be straightforward to do in Julia.
Yeah, so if you're going to do image processing, convolutional neural nets, any of the things we've talked about before in sort of modern machine learning, you're going to be using, you could be using this.
Where did I put my phone?
Seems promising, definitely.
Really?
Although Python has a big hold on, well, a lot of us are starting to use Python or have been using for a long time.
I'm going to be getting into some Raspberry Pi stuff here sooner or later, so I guess I'll have to get into Python at some point.
Yeah, like I think Jim said, this is Python on steroids.
Yeah, I think the big difference in Python, you can't do it at zero and anything network is going to be appreciated and slow. And Julia still stays fast even when you're writing loops and things.
Yeah.
Because it's compiled and all that. Actually, can Python be, can you compile, I haven't really know this, but can Python be optimized?
There's
it can be compiled or
Hey, Tim,
that's right, PYC, right? PYC.
Tim, you gotta mute your phone.
Alan, can you mute Tim?
Thanks. You can certainly optimize Python. Python runs as an interpreted language, but if you find a bottleneck in your code, you can run optimizations, or you can even run it in C.
I seem to remember PYC, or I mean, the first thing I did was do minimize to save memory, but then I thought there was Python compile PYC type. I can't remember now.
Yeah. All right. Thank you very much.
Thank you, Dr. Bruce.
Thank you, Dr. Bruce. That was great.
That was another excellent presentation.
Thank you.
Okay, so I believe our first show and tell is going to be Sergey.
Hello, everybody. Can I share my screen, please?
Yes.
Okay, and okay, not right now. I want to talk a little bit about my project in general, and then my presentation for today, 15 minutes, will be actually about NVIDIA JetBot, how to build it from scratch, from the scrap stuff that you have around your workshop, and how to make it work in simple examples that NVIDIA kindly provides, and they're very informative and very good to go through. So my project started after several runs on my lawn, 3 hours on the lawnmower motivate you very strongly to automate this process. I don't have anybody else to pass that important chore to, so I have to either do it myself or to, invent something. Of course, the lawnmower is a heavy machine, but it is a very simple when it comes to controlling it. It's 2 levers and, the throttle lever, and I created some servos to move those controls, and it runs under, generic aircraft type radio box. So if you followed me on the email threads, I post videos and I post photos, and you probably see the lawnmower running all by itself. It impresses my neighbors a lot, I feel a lot of, kind of cautious approach now. It's not like, they saw somebody just wandering around the property. Now they are afraid of the crazed rhino running them over, which is good. Now the idea of radio controlling it and, be done with it never came to my mind. Because I know how difficult it is to control it, to stay on the sticks for any amount of time. And when I was actually trying it on the lawn, I obviously discovered that when you mow a straight line and then turn around the mower, you cannot really go parallel. It's a couple of degrees off, and it leaves unmowed patches of grass, and then you have to mow it in Roomba-like fashion. I was able to mow a small patch, around here, and it's not fun, definitely. It was fun to know that it works, to know that it works for a long time, to know that nothing in the servos or anything electrical gives up smoke, so nothing overheats. So it's a solid working mechanism now, but it needs autonomous driving of some kind. What are my options? My options are GPS, of course, IMU, inertial management unit, to know the direction and position of the lawnmower and to move it using these means. The latest progress obviously is vision, and NVIDIA provides probably the best portable box for vision processing. So it's a full-blown video card that is machine learning capable, and it processes images like, there is nothing wrong with it. I obviously at some point will have to move the little NVIDIA box that I have right here to a bigger robot. First to kind of chair type of chair-sized robot, and then to the actual lawnmower. But for now, I had to create that little contraption out of scrap that I had around here. And what you see here is two motors with obviously gearboxes and wheels. And inside here, there is Adafruit Raspberry Pi motor head, which has 4 independent H bridges, and it can be controlled over I2C. So it's 2 wires that go from Raspberry Pi, or in this case, NVIDIA Jetson Nano. And then on top of it, there is a wave share box. And inside that wave share box is Jetson Nano computer. It has a little, you can see it, the power supply, which shows you voltage and amperage, and a couple of batteries, one for the wheel and stuff like that. Anybody in this session, in this Zoom session, can build something like this. It takes almost no time, and basically it is a lot of fun to experiment with it. The Jetson Nano actually runs a version of Ubuntu. It's not the latest version, it's version 18 opposed to the latest 20, but who cares, it's a full-blown good Ubuntu. And it has a lot of Jetson-specific, JetBot-specific code, which is supposed to introduce you to the power of, vision processing and machine learning as it comes to, just avoiding obstacles and detecting people and cats and whatever else. So what I'm going to do is to demonstrate in the next 7 minutes how to teleoperate it, and to just go quickly through the examples that NVIDIA provides, and maybe answer some questions. So it's a very quick demonstration. So I have everything connected now. You can see the 5 volts. I press the button here. It turns blue. Very beautiful case, by the way. I mean, WaveShare really put a lot of good thought into it, and it's what you want to have for dusty environment, not dust proof, but really nicely made and closed. Okay, so I will be putting it on the floor, and trust me that it boots now. And what I can do is I can either remote desktop from my Windows PC into the Ubuntu, or I can do SSH and use all the power of the Unix shell, or I can just use what NVIDIA suggests, which is using a Jupyter notebook with Python snippets and comments. So this is when I share my screen, and what I will be sharing is just the browser. Let me see if I can do that. And tell me if you can see the browser.
You can see it.
Okay.
Yes.
Is a resolution good enough? Because my screen is high resolution, and I don't know how it goes over the Zoom.
The images are kind of small, but the text is readable.
Yeah, and that's exactly. The image is small on my screen as well, so that's.
Sergey,
Yes.
I saw that thing you had with that programmable regulator you were using.
Yes.
So I bought one for myself. I haven't got here yet, but I bought one. It looked pretty cool little thing to have.
It's holding 6 amps very well. I know that there is a lot of chatter in Amazon reviews that it doesn't hold full 8 amps, and I haven't checked for Ripple. So it might be a high Ripple, but it.
Well, I've been keeping track of what you've been posting online there on your lawnmower robot. So.
Okay, wonderful. Thank you, Tim.
No problem.
Okay, now what an NVIDIA provides is, of course, instructions how to assemble the robot, instructions how to run examples, and all the GitHub, code you might need. And there is a very nice wiki that describes all the stuff related to the robot. So it's very friendly, and you can explore it without buying anything or trying anything. Just browsing that stuff gives you a lot of good idea. Also, if you followed my last email, I posted a link to video. It's not my video. It's some guy who is really good at presenting that stuff, and he experimented with JetBot, and the video is just much better than anything that I can present on my own. So let's go quickly through the examples. This is just the wiki page from NVIDIA. But what I will be doing is I will be connecting to the JetBot itself. Okay, Jetson 438888. And that will open a Jupyter notebook for me. So let's see if it goes well. Look at that. Now what just happened is that I connected to a server running inside my little bot that is sitting on the floor with 2 Wi-Fi antennas connected to my router, my computer connected to the router. We are obviously on the high-speed local area network, and I'm just browsing its Jupyter notebook. For those of you who never used Jupyter notebooks, it's a wonderful teaching tool and dissertation writing tool. So if you want to write your dissertation, you write some text and you write some code. You write some text and you write some code. And then when you are all done with it, it's a wonderful executable dissertation that you can send to Japan, and the wonderful Japanese scientist can double verify your results in machine learning or plotting the wonderful sine graphs or anything else. I don't know, by the way, if Julia has that type of capability. I mean, that's a very big thing in Python. Now, what NVIDIA provides is a bunch of good notebooks to try. Basic Motion will give you just control over your motors. Collision avoidance is what I went through to teach the robot to recognize my lab environment as, you know, combination of open spaces and obstacles. There is object following. For example, I can be a person, and if it wants to follow a person through the camera, it will run after me wherever I hide, doing what track roamer used to do, you know, but without nerve guns. I should probably equip this little thing with some little nerve gun. I should go through my scrap shelves. Anyway, object following, road following. Obviously, it can go through the loop. For example, if I built a little, you know, road here inside on my floor, I can teach it to follow the line or road, whatever. And teleoperation. So for this demonstration, I mean, I'm definitely over 15 minutes of time. Do you want to see the demonstration at this point? It will take probably another 5 minutes. Is it okay?
Yes.
Okay, thank you. I don't hear much objection, but hopefully.
Go right ahead.
Yeah, demo.
Demo.
So I'm double clicking on teleoperation. There is teleoperation IPy notebook file here. And when I double click it, it will open another tab in the browser, in the Jupyter notebook in this case. And you see there is a lot of explanation, and there is a snippet of the code here. Then there is a little bit explanation and the snippet of the code. And it goes like this all the time. So you can edit these snippets of the code. You can create your own notebook and put your own code in that. You can copy and paste snippets that you want, and you can paste it in the notebook that you want to try. For example, if I want teleoperation with obstacle avoidance, I can create that code completely by copying and pasting from these notebooks that are provided as examples. So what it says, create a gamepad controller. You don't see a gamepad controller on the big screen, but you probably see it on my little image, little video that is in the corner of your.
Yep, we see it.
You see it. So
yeah.
It's Xbox controllers. That's a different story actually about controllers. What I like to do is I like to standardize on my hardware. For example, when Logitech controllers were popular, I bought some Logitech controllers and they were all over my robots. And then they faded away, and now I'm, you know, well equipped with Xbox 360 controllers. If anything else pops up and I feel a need to standardize, I will. Hopefully that saves you a lot of time when you try things and use standard packages, because, you know, Xbox 360 controller is a common thing. So what I do here is I use that little area on top, which is usual for any IDE, you know, integrated development environment. And I start executing the code here in this teleoperation notebook. what happens here is that when I execute the explanation, it doesn't do anything but going to the next explanation. But then when I execute actual snippet of the code, you will see it executing, and it may display something at the bottom of this code, or it can create something visual, for example, camera, or in this case, it will create a Xbox presentation with all the buttons and everything else. So it's index 0, hopefully, will work here, because I mean, index 1 will be for another type of controller. I'm just checking the code here because I had to modify it a little bit. So let's do that. Connect gamepad and press any button. You see, so it worked. Oh, look at that. So does it beat Dr. Bruce's plotting presentation, or I still have to try harder? So now if I actually press buttons here, and there are a lot of buttons, you can see them actually, you know, some of them are controls. You see I'm moving the two sticks here, and it moves the levers.
I noticed that your buttons are also picking up the force feedback. Like if you press it really light, it only lights up half of the bar of it.
Half of the bar like this?
Yeah, like it's detecting the force feedback.
This is proportional.
Oh, the triggers, okay.
This is proportional, two proportional triggers. And the buttons are actually, they lit as they are. Anyway, I mean, that's the power, right? I mean, already you see 3 lines of code. There is a joystick, gamepad, and you can move forward. I can do a wonderful thing here. I can create new view for output. And you see that little thing goes down and still stays here. So if I press buttons here, it will be in 2 places now. But as I go through the example code and scroll down, you know, this stays. Now I will go much faster. So I hope you are already, you know, buying that Jupyter notebook and shopping for the little bot, but let me just not waste your time. So I'm pressing run, connect to robot motors. So this is a little bit of code that basically connects the sticks to the motors, and those little controls here on the screen, they are called trailets, and they are linked to a robot motor. So we create the robot object and we link the sticks. Okay, let's keep going. Now I have to turn on motors on the robot. And let me keep running. Image. So we will be showing camera. So let's go further. Should see live video feed. For whatever reason, it doesn't come. Okay, camera. Oh, here it is. And by the way, I can do the same, create view for camera, right? Now my little screen became even smaller. So I will do this. And basically I'm, connect camera to image. Stop robot if network disconnects. I'm on this snippet of code now. So there is a heartbeat, which we don't need at that moment, but who cares? And then we link the controller to the gamepad. And now let's see. And now I can explore my little lab without Okay, so that's pretty much it.
Very cool.
I hope you enjoyed that, presentation. And yet again, there is much more in these notebooks. If you start playing with this thing, you will be just blown away with the beauty and possibilities. So, any questions?
These are all the notebooks for the just for the JetBot specifically.
Yes, it is JetBot specific, and it is not really connecting to ROS or doing anything of that kind. I'm pretty sure that ROS even is not installed on JetBot as it comes out of the box. So when you download that image, it doesn't have ROS on the SD card.
Right, no ROS, right.
So it's just using Adafruit, Python libraries, and a little bit of camera, and that machine learning, whatever it is called. It's not even TensorFlow.
But you just go to the Jetson Nano web page, right, for all that.
I posted several specific links.
Oh, okay, right. Sorry.
In the email, so follow the email and you will see the links.
Thank you, Survey. Wonderful job.
Thank you.
Yeah.
Thank you, Bob.
Yeah.
Very good.
I had a question. You said you were having trouble figuring out how to make it autonomous. Have you looked into how to implement decision-making processes to once it senses something that it can make a decision based off of what it senses?
Well, yes, I did it before, and it's usually a state machine, and it's usually, what is it called, oh shoot, my memory. Maybe somebody can remind me, the way of organizing different behaviors.
Subsumption architecture?
Yes, subsumption architecture. And I implemented it before in C# on my previous robots. It works actually very well. I mean, you can organize the behavior when it goes into an obstacle, for example. It can specifically kind of pass the control to a specific behavior, for example, go around or turn around or, you know, go and mow the obstacle type of thing. So whatever else. Did I answer your question, Britt?
Sort of. So it didn't work for this one, is what you're saying? You used it in the past, but not for this?
Well, I'm very early. My lawnmower is yet, you know, not even close to receiving this Jetson Nano. You see, the progression is supposed to be like you build something big, you build something really small to understand the tools and environment. And that's my little robot that I demonstrated. Then you build something in the middle that can utilize the tools and run the actual code. In my case, it will be medium-sized robot that can go over the grass and can, you know, reliably navigate on the GPS on the big lawn, upslope, downslope. So it will be lawn mower without the mowing capability and without the noisy engine and without the 5 gallons of gas and you know, the blades. So after I'm confident with the safety and the capability of the algorithms that I put there, behaviors and the architecture, and the reliability of the whole hardware and software, I will move that little, you know, brain of it into the actual lawnmower, and that will be yet another phase of debugging and actually mowing, hopefully. Does it answer your question, Britt?
Yeah, that's very cool. So you're saying it's in the future, just not right now.
It's in the future, and I'm trying to post my progress as I go through stages, you know, and you will see it in email if I'm not, you know, a victim of another lawnmower run.
Or you can post it in the meetup, because I don't know if I'll get an email or not, too.
Well, I mean, it's 21st century. You can subscribe to email, right?
RSSC
I'll figure it out.
RSSC.
There is a lot of information there, and I keep posting not only the pictures of me on the lawnmower, but actual useful links and considerations.
Very cool. Very cool.
Cool. Thanks, Sergey.
Thank you.
We look forward for the half-hour presentation at the next meeting.
And look, Ben has an actual camera and not a scanner. He was using a scanner before as a camera.
A 3D
So
scanner.
You could barely see him, so now he's got a real camera. Good for you.
All right. So, Jim, I think you're next.
Okay, yeah. I was going to just do a fairly quick final installment of my coursework for the robotics, or the robotics nano degree program, robotics engineer from Udacity. And it's this last bit, and maybe I'll do another, you know, I'll do a longer talk if we want to do it, to go into detail, but this I'm not going to go into much detail because there's just way too many areas. But so let me start. So what this is the last project, which was called the home service robot. And let me start sharing the screen. All of this work was done on an Ubuntu 64-bit Ubuntu system, a virtual machine, which you can install using a free version of VMware, and they provided the virtual machine snapshot. So this is it. Now you should see a few windows on the screen here. including this yellow area, this yellow one that says home service robot. So, and this web page. So this project is using ROS, and it's a heavy use of ROS with lots of libraries. ROS has so much available to it. One of the main things is called the TurtleBot, which is, of course, it's a real robot, so the famous real robot system, and it's simulated in ROS so by libraries. So you can play around with a virtual version of this robot and drive it around a world. You can make a world using an editor. It's a very quick and easy way to just make walls and windows, and it's a simple editor to make a simple environment that like a building, an office, like a single floor. So what I'll show you here is some of the ROS packages that are being used to do this. This home service robot example, it's using SLAM, as well as, and that's accomplished by a ROS G mapping. So you can actually drive around this robot in virtual space and build up a map. And I showed some of this in prior meetings. It has a virtual laser LiDAR on it, and you can have virtual furniture and all that stuff and walls. And it has and this particular one has an RGBD camera, and you drive it around and it takes pictures, and it makes a map. And then you actually can drive it around using this thing called the ROS navigation stack, and that will avoid obstacles. Or I'm sorry, you can not drive it, you can tell it to go to a particular point on the map, and it will plot a path, and it uses this an algorithm, uniform cost search algorithm, to avoid obstacles. Where people may be familiar with A-star. This is a different kind of algorithm to avoid obstacles. A-star is a path planning system. And then it also uses this a probabilistic localization system called adaptive Monte Carlo. It's a long conversation about how all that works, but it uses these particles with vectors, and it spreads them all around, and using probability, it finds out the most likely the most likely one to be the actual position of the robot. This is all stems from the fact that sensors in a robot do not give actual position they don't give exact data matching reality back, and so you have to bring in probability to figure out where the robot is most likely based on noisy censored information coming back. Robots don't give you exact information that corresponds to the real world. So that's what this is all about. So anyway, whoops, did I, hold on a sec. So I'm gonna demo two demos here. Put together a shell script that launches a whole bunch of stuff in ROS, and we'll bring this one up. The first one's a navigation test, and ROS has this really fantastic program called Gazebo for simulation, and it's got an RViz, which is a visualization tool for lots of data coming in, all the sensors and maps and things like that. Now, sometimes it doesn't come up properly, so I may have to relaunch this. Yeah, the problem with having a a virtual machine is it's not quite as fast or reliable as the actual hardware, but it's a very convenient to on your Windows machine create this whole environment. Whoops, that was getting an error. Just tried this before. Okay, there's that one. On the left, you can see this is my, on the right, sorry, is the little house that I built with the editor. And then I built some furniture, and the robot is this in the middle here. This is the turtle bot. Can you see that on the right? And now on the left side is this is a map that I created by driving around the robot, this virtual robot in this walled environment. And through the laser finder, if you look at the robot, it has a laser rangefinder, or not rangefinder, but a LiDAR on it. Forgetting how to rotate. There it is. There, you can see sort of this is like a LiDAR system, or I'm sorry, that's the RGB-D camera, like an Xbox Kinect. So that drives around, collects information, and you get this map. Now, if you see all these little green arrows, those are the particles I was talking about using that adaptive Monte Carlo algorithm. So these particles are all possible locations of the robot based on the sensor data. And again, it's probabilistic. So now what I'm showing here is I can click on this thing called 2D nav goal, and I can go on the map here and make a vector. Whoops, what was that? So now what's happening is I told it, the robot, go to this location in the map, and so it is now using that ROS navigation. It is plotting, it plotted a path, and it's going to try to get there. Sometimes it gets stuck, but normally it looks like it might have got stuck. So you're seeing this visualization of it trying to do that navigation and go using the size of the robot and other factors, figuring out a path that avoids the walls. Oops, let's try that. Let me try that again. Or this is kind of getting late. Well, I just move on to the final one, which is the, so that one you can give it a location you want to go. So in this final, what is the error there? Let's try to create a new screen here, okay. So in this final example, I've already put a couple of locations, the coordinates for a drop-off and a pickup location for the robot to go to. And it's the same map, except this is now going to be completely autonomous. Gazebo, okay, gazebo's crashing. If you can see that. So now, that's not really necessary. So if you can see what's happening here, there's a pickup location where that green square is. That green square is actually is being drawn by it's a marker, and I wrote some code to draw that green square. And when the robot gets to it, it's virtually picking up the object, and you'll see it disappear. And then it will go to its final location, or its drop-off location, and then the green box will reappear. And this is done by messages. So like when the robot reaches its destination, it then like it'll say goal reached here on this little window. And then it will waits a few seconds, and now it's got a new plan and to drop off the object or clear across the house. And so now you can see how this in this graphic here, how it's trying to find a path based on the wall. It expands the size of the walls there. This is an algorithm that uses the width of the robot and buffers all the walls with the width of that, or the in this case, the diameter of the robot. You can see how these little buffer ranges are the same width of the circle of the diameter of the robot. And so that's like a danger zone, obviously, but not like it can still go through that. But then if it gets too close, it has to plot around that. So now it gets to this destination, and then you see the green square appear. Again, that is just a message being passed, sort of just to draw that green square once the robot arrives. So that's just a quick demo. I'm going to stop this share of that final project, which was really interesting and a lot of learning a lot. It's just a huge amount of information and actual practical experience with ROS. This is type of skill you can use in a job. I mean, frankly, certainly at the hobby level. But I'll give more detail about that if people want to, learn more about a specific area. I can make sure I can really present it well and simply as possible. So any questions?
I had a question. I have issues understanding the Monte Carlo. Does it work because it kind of knows what one option is and then tries to avoid it to go to the other options? Because that was my impression of it. So if it sees an arrow and says, okay, that's not it, tries to go for the other options.
That's a whole. Monte Carlo is kind of long. It's a kind of detailed conversation, but essentially it's this probabilistic locations system. So all those particles are possible locations of the robot, and they're weighted as far as based on the sensor information coming back. Like these are the ones that are closer get higher weight, or the ones that are more consistent they get a higher weight, so they become a more likely position, and based on multiple sensor information. And so then they cluster around where the robot is most likely to be, and its direction it's pointing at. So that's for localization. It's really to say, like, where is the robot where is it really in relation to the house? What coordinate is it at? Well, you can't really say for sure where it is. So with all these particles, the particles are randomized at the beginning and thrown all over the area, and then they're eliminated in multiple passes through an algorithm that kind of eliminates them based on, well, based on the sensor information, this one is clearly not anywhere close. And so then it gets down to a few sort of cluster around it. And then you kind of can take the average of that, and then this is where the robot is. This is where I'm going to say it is, even if it isn't exactly there, but it's close enough through, and that's what the probabilistic, method does. It gives you a close enough approximation between reality and the model of where you think you are, to successfully navigate. Is that a little clearer?
Yeah, it makes sense. It's like an elimination process. You kind of try to eliminate the options that you know aren't right, and then, but you said the extra part of the averaging, and that's why I wasn't thinking of for the
Yeah, now I'm a
probability.
novice to this algorithm as well, so I could prepare a little better.
No, I've learned about it before. I just forgot the averaging part. But yeah,
Oh, okay.
it makes sense now that it's an elimination process, and then what's remaining is the average. So that's really cool.
Yeah, well then you have a few left, and you can take the average of those that are anyway. Yeah,
Yeah.
Hopefully I'm correct, but
I kind of did have one other thing. Like I noticed that the square around it, its range is really big. Is there a way to kind of shape it differently so that it doesn't have to waste a lot of time of it doesn't waste a lot of energy? Yeah, like having it cut off in the back maybe, or like, moved forward the square so that it doesn't, because it probably is harder to load because of the big square.
Oh, now, yeah, again, this square is completely just a kind of a graphical flora. It's nothing real. It's essentially just drawn. It's done for purposes of illustration. There's no real. The only real thing going on with that, you can draw that square to any size you want. It's really just to simulate or to illustrate. It's not even a simulation. It's just to illustrate that if this robot were real, it would be picking up this thing and dropping it off. But all that's happening here is you're drawing a square at this location, and then when the goal is reached, or when the software, the plugin code says I've reached the pickup point, then I just turn off the square, and then when it reaches the final goal, I turn on the square and relocate it. So there's nothing really going on there that much. It's just for illustration. So you can make the square any size you want. And it's
Okay.
just,
yeah, that makes sense.
that's just for illustration. Because in this simulator, there is no way, well, I don't know, there might be a way, but there's no way at this that I know of, or that's been shown to me, that you can actually have this virtual robot pick up a 3D object and move it somewhere. That would be interesting if you, maybe in ROS you can do that, but in this case it's just simply a 2D icon.
See, I thought it was its vision range. That's what I was thinking at first.
If you're talking about this just the green square.
No, I was talking about the bigger one. I thought that was vision range.
Yeah, you're right. That is that's the navigation algorithm sort of displaying its kind of view of the world. It's not actual. This is a sort of a. I haven't read about exactly what the colors mean or whatever, but I know that border, it's expanding the walls by the size of the diameter of the robot to kind of have a buffer area, so that when it crosses there, it knows it's in danger of hitting. And then if it goes past a certain point, it won't go past a certain point. So it's kind of like a danger yellow zone, green zone, yellow zone, and red zone. That's how I would have colored it. I'm not sure, but this is a common technique is to buffer your walls, or in your navigation, to expand all the walls by the diameter, or however it is your robot is shaped, but by one diameter of the robot, so that then it knows kind of, then you don't have to add in this factor for when you're actually moving it around. You change the map, you change the way that it's interpreting the map, so that everywhere so every corner of the building is now slightly wider, and then you can just plot your path as a singular point. Normally a robot, you know, we think of a robot as a singular point in theory, but it's definitely not, it's certainly not a singular point. It's a object that has a radius or dimensions. And so if you just change your, instead of, if you want to consider it a singular point, then a dimensionless point, then you could expand the wall, you could change the map essentially everywhere to be, you know, add this diameter. And now you can use a singular point and a singular line. You saw that green line, that's just a single line for where the robot has to, or the robot's path. And because that's that's just a dimensionless line that was there, then you have to expand the walls like it's doing with these.
Yep, and so Jim, that's a great point. I hate to drain all of this information before your talk next time. We do have a hard stop at 8:15, and Britt, I think you said there was something you wanted to share with us tonight?
Yeah, but I could put it off to next time. I guess I could try to
Okay, well, thank you.
show it very quickly. But yeah, what you said made sense with the square. Let me try to share my screen then really quickly. Okay, cool. I have a lot running. It's not really related to last week's. Hopefully it should start up. It's about swarm robotics, because when I was 10 years ago, I wrote this paper. I didn't really finish it, but it was very new at the time. And after I did the paper, then the field of swarm robotics went like really crazy out, very advanced. They did a lot with it. But I shared it with someone, and it was explaining about how you use algorithms for swarms for them to be autonomous, and they kind of think like a hive mind. And each robot is called a boid, and it uses biomimicry, because the swarm robotics is taken from sometimes ants, because they leave a chemical signal behind, and it's a communication to the next boid, which would be an ant, or bees. And so what I was thinking about was like, how do you use swarm robotics? And me, I like learning about bionics. So I was thinking there's something called claytronics, where the boids are just so small that they can assemble like clay to form objects, like ants forming a bridge together. And so it says, like ants creating a bridge, they form an object, and then they have the capability to act like a single robot while maintaining the characteristics of swarms and boids. So you have like one big robot that it forms, but each individual robot in it, the boids, still have their own sense of self, the individuality. And that's the thing about swarm robotics. You have the individuality of each robot, kind of like cells in a body, and then you have what it creates. And that's kind of like a robot in itself too, kind of like the human, like a body, you know? So I was thinking maybe it could be the future of prosthetics, where you can have maybe claytronics, where you have the robots, swarm robots, forming whatever you need, like an arm, replacement arm or leg. And yeah, it probably could have specialization of like muscle or bone. Yeah. And then they would have like, sometimes they would make helicopters, form patterns and stuff in space too. And that one was called second order robots, because they form a lattice. In material science, lattices are patterns that show the layout of a crystal. But in this one case, it's robots forming like the pattern of the larger robot, and that's with the claytronics. And this would be like nanobots. Nanobots would most likely be the claytronics. So if nanorobotics gets improves, then they could start doing claytronics. And so this is kind of what it looks like when there's an issue.
It looks
Yeah.
like your paper is not coming up right now, so maybe we can continue.
It's not?
Yeah, we're just looking at a circle. I don't see any paper or anything.
Really?
I just see your Windows Explorer with finalpaper.pdf selected.
Give me a second then. I'll try to share it again. Here, that's better. So yeah, it shows like what it looks like, an individual robot trying to get to a problem, like say this one was like a chemical spell, and this is how it has to work it has to do the work of all the different robots, so it has to map like the entire area before it gets to what it needs to. But the swarms, they can specialize. See, these are the blue ones because they found the signal, and it's like a hive mind where each the thing about swarm robotics is that each individual has the same algorithm applied to them, and because they have the same algorithm applied to them, they are able to that's what allows them to act as a group. And so they have once they go by the same roles, then they could help each other out. And so when they get the signal, only a few need the signal, and then they all get to what they need. It makes things very it speeds up the problem solving. So like here, this one's a flock, and is what they call a group of these swarm robotics, and the roles that they have is avoiding bumping, maintaining the same speed for all individuals, and they stay close to each other. That's how they kind of act like one, but maintain their individuality. And yeah, it allows for a lot of simplicity, because now each one of them has a small role. They don't have to do they only need to do one task, and then they all get the message and go with what they need to do. And see, they then they each can do different different roles and very quickly. And this says it allows for error. So if a robot breaks down, then the other modules can carry on the same task. Why? Because they all have the same role. So it's there's no learning curve, and that's why it's simple.
Right, I see. So Britt, were you here a few meetings ago when Dr. Morales was talking about his swarm project? Did you see some of the stuff that he was doing?
I might have been there, but I might have showed up late.
Okay, yeah, no problem. I think we recently posted some of his papers, so I think you will might get a lot out of it. He's doing some very interesting work right now in swarm and cooperative task solving.
That's cool. Yeah. Maybe I'll go see it. It's in the email list.
I believe it was posted to the group. Yeah. for sure.
Okay, I could
Yeah,
check
it's
it out.
there.
I guess there's one last part of the essay that when you need to have focus, it's a lot nicer when you have one robot just focusing. But the problem with groups is that it's not always productive, where you have to maintain uniformity in a group. And unfortunately, when everyone starts doing the same thing, communication can get lost, and then they start breaking into smaller groups and counteracting each other's work. Yeah, so there you go. That was a small amount. Yeah. That was my small story.
All right. Well, Britt, thank you so much for sharing that. That's swarm robotics and the intelligence and the program that is actually a very popular topic right now. I'm looking forward to see what you and Dr. Morales both are up to in upcoming months.
Yeah, I think it's it aligns with drone technology because they have the air swarms.
Yeah.
Because there's bees and stuff. Yeah, there's the land swarms like with ants, and then the bee swarms like in the
So,
air.
Britt,
Yeah.
can you possibly submit that to be posted on our site?
I could try to look into it because it was like a class assignment that I submitted, but I think I could post it. I don't see an issue now because that was a long time ago. So yeah, yeah, I could post it in the email list.
All right. So if you need any help with that, let us know. I'd love to take a closer look at it. Britt, thanks again for sharing today. That was super cool. And thanks to everyone for joining and for Dr. Bruce. We have a hard stop at 8:30 tonight, so this is about perfect. Chris has graciously volunteered to move his show and tell to our next meeting on the 24th. So I look forward to seeing more about that then. So thanks everyone so much for joining. Hopefully you're doing well and healthy, and everyone in your circle is doing the same. And we'll catch up in a couple of weeks. Ben, you have anything to add?
Right now, you'll see that my robot is finally standing up on its own.
Oh, I need to see that next time for sure. Check that out.
Okay, guys.
All right, Ben, you have anything to add?
That was it. Thanks, everybody. Stay safe
thank
and
you.
All right.
healthy.
Do show and tell next time.
Thank you.
Yep.
All right. See you guys later.
Take care, everyone.
Take care, Sergey.
Stay happy and healthy. Bye-bye.
Okay.